So let me start with a poll. Who's kind of thinks of themselves as reasonably familiar with IME? You've been presented to before? Yeah, okay. It's about a quarter of the audience. Okay, so I'm going to brief you on what we have today, or at least very shortly, IME 1.1. So that's coming out late this summer. Currently we are GA with 1.0, and at 1.1 will bring a few new features and new hardware into play. So I'm going to briefly cover, what the mechanics are behind IME, talk about the new features and the new performance attributes of that system. So here is a kind of a rather detailed problem statement. The applications are all changing, and they're perpetually changing. And today we see a problem of the file systems not really matching the changes in application characteristics. So there's just a little select set of examples, what we're seeing in the increasing sophistication of research applications emerging today, and actually have been for the past decade. So for example, we have lots of multiphysics out there. We have adaptive mesh refinements. We have machine learning, higher concurrency due to the introduction of GPUs, many core CPUs, etc. And more complex and larger workflows and ensembles. So that all seems like a compute problem, but in fact it all presents different I/O patterns down to the file system. And in fact, the file system is really not structured to cope with these changes. So for example, with multiphysics or adaptive mesh refinement, it's quite a difficult, complex procedure for an application developer who's got a lot of things to worry about, to also then worry about how he matches his in-memory block size with the file system in order to get maximum efficiency. And furthermore, it's even more difficult for them to do that when they're running on 5 nodes, 10 nodes, 100 nodes. And it's even more difficult if they're doing multiple different models, different physics, different algorithms within the same application. And so these all bring various issues with current file systems, and these are some of the things we try to overcome with IME. So hopefully the only image you won't come away with after today is a picture of a duck, but I wanted to just highlight one of the kind of main advantages of IME. So this is your typical application, and it does kind of what it does, and it's had long-term evolved characteristics to do what it does. And we kind of understand that the vast majority of applications out there aren't really the exascale ones, which do get rewritten, re-optimized for every machine that comes along. A lot of these codes have had many years, 10, 15 years of evolution to do exactly what they should do. They've already been optimized for various attributes, like for moving to many core from 1 or 2 cores a few years ago, to cope with a higher network bandwidth, different memory hierarchies. And one of the problems is it's very difficult for us to come along with a new file system and say, okay, please can you also optimize your application again, not only for all these compute side attributes, but also for the file system attributes to optimize the I/O patterns. So really one of the ways that IME is trying to attack this problem is by making the underlying platform accelerate the application, whilst minimizing the overhead to the application developers. And this is, we don't do everything perfectly, but this is essentially what we're trying to do with IME, minimize the interruption to users and maximize the performance gain. So back to basics about what IME is and what the basic structure is. We start off with some compute on the left-hand side and a parallel file system on the right-hand side. And we insert into the middle of that a new layer, a layer based on NVMe or flash, NAND flash today. We introduce it in such a fashion that this whole flash layer, which inherently gives you low latency, very high IOPS, can be exposed directly to the application. Now remember, if we were to introduce that flash below the file system, or indeed below the controller, then we've got many layers above us. So by introducing this layer in front of the file system as an I/O system that manages the I/O before it gets to the file system, we can do more things. And we can do more things to take advantage of that low latency, high IOPS metadata or media underneath us. So on the compute nodes over there's some IME clients. So we intercept the I/O directly from the compute nodes, directly from the application. We send that across the network in these fragments to our IME layer. And then later on, either through an API controlled by the scheduling system or the user, or through IME automated policies, we'll manage the data movements to and from the backing file system. So we have 2 major models. One, we totally minimize any user involvement in the introduction of this new cache layer. So there's no a fundamental requirement for a user to understand this hierarchy below them. But we do give you the APIs and tools to enable you to optimize the efficiency of a system, let's say for an exascale system, a single-purpose machine, where you can add additional hints and, for example, prefetch, purposefully stage the data back and forth through this burst buffer. And why would we do that? In fact, there's a set of probably 15 use cases, and because I didn't want to take all day, I just summarized a couple of these use cases. The prototype use case for a burst buffer is as something that will absorb the large spikes and allow the backing file system to take the background load. And here's an example from Argonne where they measured the file system activity. And as you can see, and probably as you all expect, we're seeing peaks up to the maximum performance of the file system, but in fact the background load is around 5% of the time where we're using a very small fraction, only a tiny proportion of the time are using all that throughput capability of the file system. So instead of speccing your file system to meet the maximum throughput of individual applications, which might only peak for 1% of the time, you use a burst buffer for this purpose, and the file system manages the background load. So that's kind of use case 1 out of a set of 15, let's say. So use case 2 is this caching problem. So currently we actually rely upon file system caches to accelerate our data. And this is usually a client cache. So for example, with GPFS, we have a client cache, and as long as we can fit our problem size into this client cache, we can go really fast. The issue is that the problem sizes are getting much, much larger, and it's very expensive still to implement very large RAM inside of these clients. So I took a snapshot actually from Sanger's mouse FTP genome site, and here you can see some fairly small examples actually of some very large BAM files, so genome files for various attributes of mice. So here we see 182 gig, 112 gig, 138 gig. So already we're seeing just this typical snapshot exceeding the capabilities of compute node memory. And IME attacks this problem too. So we provide this fast, flash-based burst buffer layer that allows to burst out of the node to a remote shared file system and access those IOPS quickly when they can't fit in this cache. So a couple of little use cases. So really I wanted to introduce you to the broad set of use cases in just one slide. So if I want to summarize IME's capabilities, then here they are. We have this single shared namespace to all clients. That's quite differentiated compared to other burst buffers. When you implement IME, you see the whole backing file system. All clients see everything. And that means workflows are very easy to implement because every node, every application, every client can see every file which has been issued or read from every other node. On the left-hand side, you see the I/O challenges we do particularly well at. So at its base level, IME tends to compete extremely well with the parallel file system for a given number of SSDs. But for a certain fairly large subset of problems, we do extremely well. So those are characterized by random I/O, random reads, random writes. We do very well by reducing the path, the I/O path, between application and safety on this SSD layer. Shared file I/O, we'll see an example later on. We do extremely well by obviating the file system locking mechanisms that are normally incurred when you're doing parallel I/O to a shared file. And then high concurrency, partially because we're just using SSDs and the IOPS capability is very fast, and partially because we have this new software layer, we can really sustain our performance through very high thread I/O levels. And if we look at a parallel file system with hard drives, what you see is a peak. You increase the number of threads, and you get steadily increasing performance. Then you hit a peak, and then there will be some degradation as we start seeing disk thrashing occurring in the backing file system. So we obviate that problem. So essentially, across all those workloads, the consequence is that you see more of the peak performance more of the time with an IME cache layer because we remove some of these bottlenecks incurred by the file system. In terms of features, then we have this very high Y-speed throughput, very high IOPS, but there's a few additional features that we'll be able to implement because this is a ground-up software development. So for the past 5 years, we've really started from scratch and implemented this whole software infrastructure. So for example, we've got adaptive I/O. The I/O can in real time work around bottlenecks that appear within the file system or within the underlying infrastructure. So if a server is busy, then we can send the I/O in a different ratio around that busy server so that we're not subject to Amdahl's law. And that's where the slowest thing incurs a heavy penalty on the complete file system load. So we get rid of that problem, and the system will always perform at the performance of the underlying devices, rather than being penalized by one specific device being slow. The rebuild speeds are very, very fast. So currently we're seeing around a terabyte SSD rebuild in a small number of minutes. And I'm talking about 2 or 3 minutes for a terabyte SSD rebuild speed. And that's due to completely declustered across multiple servers, and the SSD management gives us this very, very fast rebuild speeds for single SSDs. So 1.1 brings us this IME 240. It's a 2U system. It's got up to 23 NVMe drives inside. And the performance characteristics are pretty strong. So here we see an example of, you can't probably read this, but you've got 4K file per process, 1 meg file per process, and the same for single shared file. The point of this graph here is to show you, so on the far right, you'll see what happens if we just look at the specs of the drives. These are P3520 drives from Intel. If we look at the specifications and we multiply it by the number of drives in this system, then we get these numbers on the right-hand side for writes and reads. What we've done here is we've run a benchmark across multiple clients and measured what the clients see to this system. And you can see we're slightly exceeding even the theoretical peak performance of the SSDs, both with 4K IOs and 1 meg IOs from these clients. So we're getting more than 100% of the peak performance. And part of the reason why that is because of the mechanics, the internal mechanics. So it's a detailed conversation, but we can have it. But we're doing extremely well in terms of delivering the underlying efficiency of the SSDs directly to a set of clients running benchmarks or applications. So this IME 240 system, it's 2U high, and here we see a couple of benchmarks which look at the performance of that across a range of IO sizes, shared file, and file per process. These two different sort of IO paradigms we have in high-performance computing. And we do that through MPIO and through POSIX. So there's no application changes necessary. We can take an application off the shelf and run it on this IME platform. So here we see with 2 devices, we're exceeding around 46 gigabytes a second. That's around 23 gigabytes a second per IME 240. And we've also plotted the luster plots here, which is the lower green and blue lines here. So the upper 4 lines you can see here are all MPIO or POSIX, 1 meg and smaller IO sizes. And then the lower lines here are what we get for the luster system. The major point here is that in this case, the IME 240 system is 4U, and the luster system is about 30 rack units. So we're getting very, very high performance, approximately 10x per rack unit per gigabyte per second in this case. The more dramatic case, though, is this shared file case. So when we have checkpointing, for example, or many other use cases in high-performance computing, we're performing I/O into a shared file. And with IME, we're obviating the underlying file system locking processes. And you can see that right here. So here we're getting 43 gigabytes a second from these 2 systems, and that remains very consistent, even down to very small I/O sizes of 32K. We're still getting over 10 gigabytes a second, nearly 15 gigabytes a second from just 4K IOs. When we perform the same workload, the same shared file workload against luster, then we see that's where the penalty is incurred through this parallel file system locking, which we obviate through IME. So that's just one example, and we have other examples. It's too long to go into them in detail, but one example of a very strong use case for implementing IME on top of a parallel file system. Here's a real-world example. So we were actually sent this benchmark by a customer. It's a Warf benchmark. This is a weather benchmark, very popular open source benchmark. Anybody who's familiar with Warf in the audience? I think there's quite a lot of you. Yes, it's pretty popular. We ran this on a fairly large system, which has a 200 gigabyte a second luster file system underneath, and about 400 gigabyte a second IME system. And we increased the I/O load on that system, so it's doing checkpointing, it's doing very fine meshes, it's doing a very heavy I/O proportion to the compute proportion within that load. We get about a 17.2 speed up in the I/O times comparing across luster and IME. And that's really to do with this random I/O effect and this particularly the shared file I/O effect. And that has an overall runtime impact of a 3.5x speed up. So a couple of extra features that come out with 1.1. So this system's been in production, or at least the IME 1.0 has been in production now for since late last year. In September, we're introducing IME 1.1, and that brings us a few more features. So firstly, we're supporting EDR, OPA, and Ethernet up to 100 gigabit Ethernet networks with IME 1.1. Secondly, we've really gone a step forward in terms of how we allow your applications to define the data protection levels. So there is in IME a default erasure coding level, and you set that according to the number of nodes you have and then what you can afford to erase your code. So for example, you might have a default erasure coding level with 10 nodes of 8 plus 2. Therefore, if you lose a couple of nodes, you've still got production data. But beyond that, with IME, we allow the applications to select their own erasure coding level, if they so desire. So in this case, we're seeing a diagram which shows a set of, let's say, 10 applications, and each one's choosing to do a different erasure coding level according to how much protection it wants against SSD failure or node failure during the runtime of that job. So dial-in, flexible, adaptive erasure coding is one of the major new features within IME 1.1. And secondly, it's node failure management. In IME 1.1, we manage whole node failures in this cache layer. So I mentioned we already do these SSD rebuilds in about a terabyte in 2 or 3 minutes. Whole node failures are now covered within IME 1.1. So we have a erasure coding level. In this case, let's say we have 4 nodes, and we implement erasure coding of, let's say, 3 plus 1. That means we can lose one server, and we still have enough data to reconstruct that stuff. We can continue the I/O service when a node fails, and as there's reads to the data that has been lost, that will be rebuilt in real time to serve the incoming read requests. So there's a new level of data resilience against failures. Whilst these node failures are going on, we can also incur SSD failures. And as I said before, those will be rebuilt with full resilience within a few minutes anyway. So the maximum parity level is 3. So 8 plus 3. We're going to step up from what we have with traditional RAID 6, and also it's adaptive and flexible according to the application. There's more complex areas with more servers, and you can have higher erasure coding levels to cope with more failures than that. So in summary, we've got this IME 240 system delivered with IME 1.1 out in September. We have a new set of dial-in parity available per application. Applications can choose their parity level. We have adaptive I/O that works around bottlenecks and high loads within the system. We've got very fast rebuild speeds, around a terabyte in a small number of minutes. Kind of depends on the erasure coding level, number of servers, etc. And then it's flash native, so we minimize this write amplification problem. So if you have a SSD with a limited endurance level, that endurance level is actually calculated based on random 4K writes. We're flash native, and that means we have a log structured file system. This means we never do 4K random writes. We're always doing rather pleasant 128K sequential writes to that system. And that really maximizes the lifetime of the SSD and also maintains a consistent performance level for these SSDs. And I'm going to pass over now to Rosemary from Alexis. So this is IME 240. You can come and talk to us in the booth. We have 4 systems right there. They're running applications right now. We're getting very close to 80 gigabytes a second from just a small set of 8 clients down there over an EDR network. So come and have a look at that and talk to myself or Jean Thomas, who's in the audience, I think, somewhere. There he is. And we'll be glad to do a demo for you. Thank you very much.